In section 4.7, we will review our old friend, the limit. There are some limits that we couldn't do before, and with Hopital's rule, we will be able to find these limits. Hopital's rule is useful when you have what's called indeterminate forms. So when you have the case where you're looking for a limit and you get some sort of 0 over 0, we will be able to use Hopital's rule. Now, in order to use Hopital's rule, you must have an indeterminate form. You cannot, you know, these conditions must hold in order to use Hopital's rule, meaning that I must have this 0 over 0 indeterminate form. Alright, so once it's been established that the limit produces some indeterminate form, then Hopital's rule says that I can take the derivative of f and the derivative of g and find the limit of that entire function, and it will be the identical limit. Now, this theorem is proven using the mean value theorem and a bit of geometry, and in the interest of time we'll skip over that, but it is in section 4.7 of the text. Alright, let's first off look to see if we can find this limit. We're going to try direct substitution. I will get 1 cubed plus 1 squared minus 2 over 1 minus 1. I'm going to get some 0 over 0 form. Therefore, I can use Hopital's rule. And I am going to take the derivative of both f and g and see if I can find the limit then. Derivative of f is 3x squared. Now note that I'm not taking the derivative of the quotient. This says to take the derivative of each one. We're not taking the derivative of this thing as a function. And then the derivative of this is going to be a 1. Plugging in a 1 because now I can. This is going to be 3 squared plus 2 times 1 minus 2. This answer is going to be 3. And if you'll graph that function, you can see that that is your limit when x is 1. Let's play again. We're going to try this with direct substitution. And we will get square root of 9 plus 0 minus 3 all over 0. This gives me 3 minus 3, which is 0 over 0. I can therefore use Hopital's rule. So I will take the limit of each one and then see if I can do direct substitution or one of my other little techniques. Derivative of this, the 1/2 comes out front. Then the derivative of, I leave the inside alone, plus 3x minus 1/2 times the derivative of the inside. Derivative of the inside is a 3. That constant term drops, and then this would be a 1. Oh, that makes it nice, doesn't it? So I can just do direct substitution because I don't have, well, I might have something in the denominator, 3 times 0. I'm not going to have anything. I can still do my direct substitution. 3 over 2 times the square root of 9 plus 3 times 0. That's what I have here. So that's going to be 3 over 2 times 3 is 6. So this guy is going to be 1/2. Nice. I can do these limits without having to. Do you remember before we used some algebra techniques here to see if we could find limits? We would have factored here to see if we could find limits there. Alright, they call this Hopital's rule repeated because another trick you can use is you see if you have that indeterminate form of 0 over 0. Well, I'll just show you. Let's just play. I'm going to see if I can plug in here e to the 0 is going to be 1 minus 0 minus 1 all over 0 squared. This gives me a 0 over 0, therefore I can use the Hopital because that indeterminate form condition is satisfied. I'm going to take the limit as x goes to 0, and then I'll take the derivative of the numerator and then the derivative of the denominator. This is e to the x minus 1 over 2x. I'm now going to try direct substitution. I will get a 1 minus 1 over 0. I get 0 over 0 again, meaning that I can use, since I have an indeterminate form, I can now use the Hopital. So I will take the limit as x goes to 0, and I will take the derivative of the numerator and the denominator and see if I can do direct substitution now. This would be a plugging in a 0, 1 over 2. Oh, that was nice. Alright, let's play here. Oh, I've got several powers here. Hopefully this will work out nicely. If it doesn't, then I have to do other techniques. Let's see, I'm going to do a direct substitution hold. Okay, trying direct substitution. 2 cubed minus 3 times 2 squared plus 4 over 2 to the 4th minus 4 times 2 cubed plus 7 times 2 squared minus 12 times 2 plus 12. Crunch those numbers on your calculator and you will find that this is in the form 0 over 0, which means I can now use L'Hopital's rule. So I will take the limit as x goes to 2, and I will 3x squared minus 6x, 4x cubed minus 12x squared plus 14x minus 12. And I will see if I can do direct substitution. So I'm going to plug in a 2 here. I will get, let's see, 3 times 2 squared minus 6 times 2 all over 4 times 2 cubed minus 12 times 2 squared plus 14 times 2 minus 12. And I crunch this again, and you will get 0 over 0. Since it's still in this indeterminate form, I can use the Hopital one more time. Hopefully I won't have to use it more than once, but I might. Limit is x goes to 2. 6x minus 6 over 12x squared. I'll write it down. Ah yes, and now when you plug in a 2, you will get 3 over 7, which will be your limit. And you can look at the graph of that and see. L'Hopital's rule can be extended for your infinity over infinity cases of positive, negative doesn't matter. Just if it's an infinity over infinity case, L'Hopital's rule can be extended. Now the proof of this is not included in your textbook. You will have to wait till you get into more advanced mathematics before you get to look at the proof of this. I know you can't wait to get there. But just note that you can use this theorem in finding your limits. We don't have to try any of our other factoring or multiplying or finagling techniques. If I have this infinity over infinity case, which I do here, and if you'll note, I'm looking at this function, really if I look at it as horizontal isotopes, which we have, I notice that this one is evenly balanced. So I already know that it's going to 2, but let's use L'Hopital's rule to prove it. Alright, so if I plug in infinity here, I will get that this is infinity over infinity. So I'll use L'Hopital, and I will then say that it equals the limit as x goes to infinity. Take the derivative of both the numerator and the denominator, and I'll write that down. Okay, got it. Once again, I'm going to try to plug in infinity, and you'll see that I get this infinity over infinity case here, which means I can use the Hopital's rule one more time, and I'll write that down. Alright, we're back. Putting in this infinity here, I get another infinity over infinity case, which means I can once again apply the Hopital's rule. And I have taken those derivatives, and now I have that this is a constant, and the limit is then 2. Next little guy, if I plug in a pi over 2, now I'm looking at this from the left, and so if I look at this from the left, you can look at these on your graphs, what have you. I will see that this case goes to an infinity over infinity, which means that I can then apply L'Hopital's rule, which means I'll have limit as x goes to pi over 2 from the left, and then I'll take the derivative of both the numerator and the denominator. Derivative of tangent is secant squared. The derivative of secant is secant tangent. This simplifies a little bit, so I'm going to go ahead and do that. Limit as x goes to pi over 2 from the left. I'm just going to have a secant x over a tangent x. And this simplifies because I will now have limit as x goes to pi over 2 from the left, 1 over cosine x and sine over cosine. Meaning these two cancel, leaving me with limit as x goes to pi over 2 from the left, 1 over sine is then going to be 1. Nice. Now note that we could use the Hopital's rule if we had the indeterminate form 0 over 0 or infinity over infinity. We did not have a rule for this particular case or this particular case. There are some little tricks we can use to make it be in this form, but we don't have a theorem for either of those two cases. We can see if we can piddle with it a little bit and maybe get it into something that would be in this form. So that's what this first example is about. If I look at x squared as 1 over x squared, maybe I can do something with that. If you'll notice in this case, I actually have an infinity times 0 case, which L'Hopital's rule doesn't apply for this one. So let me rework it, just piddle with it a little bit, making that x squared, instead of it being infinity, maybe I can make it look like something else. Limit as x goes to infinity of 1 over x squared, and then let's just put this sign in top, sine of 1 over 4x squared, because he's in the numerator anyway, so let's just write him there. Now, where before I had infinity times 0, even though this is still x squared, because it's 1 over x squared, it's still x squared, this limit now looks like 0 over 0. Because of that, I can use the Hopital's rule in this form, and it has to be in this form, as x goes to infinity. And I'm going to take the derivative of the numerator and then the derivative of the denominator. Using the chain rule, I'll write that down. Alright, after taking the derivative of each and then simplifying a little bit, I'll get the limit as x goes to infinity, this thing goes to 0, cosine of that thing goes to 1, and then this would equal 1/4. Pretty good. Alright, I'm going to wiggle with this one a little bit because it is going to be in the form of infinity and minus infinity, and we can't use the Hopital's rule on that. So we got to wiggle with this thing a little bit so that we can use the Hopital's rule and make it either be infinity over infinity or 0 over 0, something of that sort. I notice I got an awful lot of x's in here, so what I'm going to try to do is, and I know I have this square root, so I'll be looking at maybe, I think I'll look at pulling an x out of there. Square root of x times x minus 3. Okay, so I'm sitting here, and what I'd really like is to pull out so that I can have an x over here. So if I pulled out another x, I'll make it so it'll be a little better, because that doesn't help me much. So I'll look at piddling with it a little bit more. Maybe if I pulled out an x squared, so that then I could get some factors anyway. So I pulled out an x squared, then I'd have 1 minus 3 over x. And I like to have those x's in the denominator, especially when I'm looking at infinity, because that thing goes to 0. It makes it nice. So let's keep working with it. Keep piddling with it until you get it in some form. I'm still looking at it. I still have it in a infinity minus infinity form. But now I can pull this x outside of that square root, and then I'll just have a 1 minus 3 over x inside. Okay. Still can't do anything with it. Keep piddling. I'm going to pull out that x. Now I have factors, and that's the key. So you want factors, because if I have factors, I can play the same game that I did upstairs right here, and I will just divide. I will say that x is 1 over x, so and I will have 1 minus 3 over x in the numerator, and then the denominator will have 1 over x. In this case, that goes to 0. I have a 1 minus 1, so I have a 0 over 0 in the numerator and a 0 in the denominator. Oh man, I can now use the Hopital's rule. So 0 over 0, I can use the Hopital. That means I'm going to, in this form, take the derivative of the numerator and the derivative of the denominator and see if I can get something from there. Okay, I took the derivative of the numerator and the denominator using the chain rule. Now I had these x squareds that are going to cancel, and this negative is going to be a positive, so I'm going to have this 3 halves over square root of 1 minus 3 over x. And with direct substitution, this goes to 0. Square root of 1 is 1. This thing goes to 3 halves. And it's not like it was easy to get there, but I got there. The thing is, I'm capable of getting there with the Hopital's rule. Alright, this is another way to wiggle ourselves around in order to get a limit. We've been doing this with this x to the x for some time now. We rewrite x to the x as e to the x natural log of x using our log properties. It's basically using that fact, and that's what you're doing in this procedure 1. So first off, we need to get what L is, and L says, and I'm just using this right here, where g of x is x and f of x is x in our case. So let me just go ahead and write that down, that f of x equals x and g of x equals x. This procedure tells me to write it as the limit as x goes to 0 plus of g of x, well that's x, natural log of x. Okay, now once I have this, I can see that 0 plus. I can see that I don't have any form that I can use the Hopital with. So I'm just like, well, okay, can I rewrite? Ooh, I've got this product here, so guess what I'm going to do with that guy? Do what I did in the previous example. Natural log of x over 1 over x. That will allow me, because 0 from the right, then this guy is going to infinity, and this guy here with the 0 in the denominator, that's going to infinity, so I have this infinity over infinity form, meaning I can use the Hopital. So I'm going to take the derivative of each one and see what I can do with that. Derivative of this is 1 over x. The derivative of this, that one would be minus 1 over x squared. Piddling with that, just simplifying it, I get the limit as x goes to 0 plus, and that would be of negative x, and I can do substitution on that, I think, and get 0. Now there's another step to this. That's not your answer because you had to rewrite it. Your answer is the limit as x goes to 0 from the right of x to the x is going to be e to whatever number that you got here, and this happens to be 0, and there you have it. Now we're going to try this again for our next one. And let me just go ahead and note that this was in the form 0 to the 0, which was this one right here. Our next one is going to be, if I plug in an infinity, it's going to be 1 raised to the infinity. So we're going to have this case right there. Okay, let's look at this closely. I'm going to have the f of x is this 1 plus 1 over x. G of x is once again x. Okay. I'm supposed to find this L. And this L is the limit. And I did have the 1 to the infinity power here. So I'm able to use this procedure. It goes to infinity. And it tells me to take g of x, that's x, and then the natural log of f of x, which is plus 1 over x. Now I'm still not in the appropriate form, so I'm going to rewrite this just a little bit so I can use the Hopital's rule, because I have my products here. Limit as x goes to infinity of the natural log of 1 plus 1 over x over 1 over x. Now I'll be able to use the Hopital's rule, because now I'm going to have I'll put in a infinity here, that'll be a 0, natural log of 1, that's a 0, put in an infinity here, that's a 0, I have a 0 over 0 form, so 0 over 0 form, I can use the Hopital for this, at this section, juncture here. So I'm going to take the derivative and then I'll simplify. Alright, so I took my derivatives, I found very sweetly that this happens. I'm now going to get, I can do my substitution, because when I plug in an infinity that goes to 0, I'll have 1 over 1. This thing is 1. I'm not finished yet. I still have to do part 2, which says that the limit as x goes to infinity, you got to do the e to the 1 plus 1 over x to the x is e to whatever power you got. I got a 1, so this thing just equals an e as its number. In this next section of content, we're comparing functions that both go to infinity. So if I look at this one right here, this would go to 0 if both f and g, understand, as x is going to infinity, both of them are going to infinity, but one of them is going to infinity faster. So if f is going to infinity faster than g, then the limit goes to 0. However, if, well, when we just keep it, f is growing faster, I said it right there, and then we put f on top when we say that he's growing faster, then the limit would then go to infinity. If they're both going to infinity at the same rate, then we would that would be like an evenly balanced function. We'll go back to this theorem in just a minute. We're going to compare the natural log function and x to any power, and we're going to see which one gets bigger faster. Alright, so I want to compare and see which one is getting bigger faster. So I'll just put, as x goes to infinity, natural log of x over x raised to some power, some number. As of right now, I have an infinity over infinity. Both are going to infinity. I can use the Hopital's rule, and that does need to be stated. And if you do your show your work, be sure and state that. Say it is going to one of the Hopital rule's conditions, and therefore I can use it. So now I'll take the limit as x goes to infinity of 1 over x, and this will be p x to some p minus 1 power. If you'll notice, I have an x in the denominator here. When I combine it with this guy, I get the limit as x goes to infinity of 1 over px. This thing is going to 0. That means x to raise to some power is getting bigger faster than the natural log, and that's how I'm comparing. In this next one, we're comparing, seeing as natural log didn't grow as fast as the powers of x. Let's just see if we can take and raise the natural log to powers and see if it gets bigger just as fast. So that's what we're looking at doing, and we're going to compare basically the powers of the natural log of x. So I'll just put it to the power q, and x is going to be raised to some p. I'll rewrite this. I'm just going to rig it a little bit so that I have limit as x goes to infinity, the natural log of x over x to some p divided by q. And then all of this I'll raise to the q. I already know what the answer to this is. I just found it in that problem. The natural log of x over x to whatever power is going to 0. So 0 to the q power still equals 0. Done with that one. Since we already know some things about natural log, we could rewrite this with dummy variables and just say that here we have the natural log, whatever power p of t, and then we'll just call this t. So we'll rewrite the top one in terms of natural log. We're just rewriting them using the definition of log basically. And in this case, I already know what the answer is because I got it in that one. This means that e to the x is getting bigger a lot faster than x to any power. So looking at this theorem here, it's just showing the range of power on who gets bigger faster, and we can see that x to the x gets bigger faster than any constant number to an x. That makes sense. That constant number to a variable power gets bigger faster than x raised to some constant power, and so forth. Here's some of the common places that people make mistakes. One of them is be sure that you have this indeterminate form. You have to have that indeterminate form. Be sure that in showing your work you tell me that I have the indeterminate form, then I can use the Hopital's rule. Another is don't do the quotient rule. You take the derivative of the numerator and you take the derivative of the denominator. It's much easier that way. Don't make it harder on yourself than it really is. And another thing is be sure and simplify, because if you don't simplify, then sometimes you're sitting there with still an indeterminate form, when if you would have simplified, you wouldn't have had that indeterminate form. So go ahead and cancel things and add and subtract things out as needed. Sometimes the Hopital's rule isn't going to work for you. Sorry. That's what this one is about. Sometimes you keep doing it and you just keep getting into this cycle. Anyway, that's it for the Hopital. I'll see you at the Collaborator. Email me if you have any questions.